We've gotten to one of the fun parts of this lecture, collisions. A collision is just what it sounds like, bodies colliding into each other. This can be cars, billiard balls, objects in space, neutrons hitting atomic nuclei in a nuclear reactor. Anytime the forces between the colliding objects are much greater than any external forces that may be present, we can neglect the external forces and treat the collision as an isolated system. Thus, as we just learned, momentum is conserved. Remember, when momentum is conserved, it just means that the total momentum of the system isn't changing from one moment to the next. This means that we can pick a moment before the collision, say of these two objects here, A and B, and then a moment after they collide, and set their combined before and after momentum equal to each other. So moment 1 is before the collision, and moment 2 is after. So we can have the momentum of A before plus the momentum of B before set equal to the momentum of A after plus the momentum of B after. And if we write all that out, momentum is ma, so ma va1 plus mb vb1 is equal to ma va2 plus mb vb2. There are two types of collisions, elastic and inelastic. Elastic collisions are ones in which the total mechanical energy of the system stays the same through the collision. None of the mechanical energy of the colliding bodies is transferred to other forms of energy, like usually heat. This never happens completely, but there are many collisions that lose such a negligible amount of mechanical energy that they are almost completely elastic, and we can safely treat them as if they were elastic. For elastic collisions, not only is the total momentum of the system conserved, but also the total kinetic energy of the system. The other type of collision, inelastic, makes up pretty much every real collision in the universe because pretty much every collision loses some mechanical energy to heat upon collision. An inelastic collision is one in which the total mechanical energy of the system then does decrease. Dropping a meatball onto your plate of spaghetti is an inelastic collision because the total mechanical energy of the system has dropped to zero once your meatball settles. In fact, this is what we call a completely inelastic collision because the two colliding bodies stick together. In this case, we would rewrite our momentum conservation equation, or the equation that we get from momentum conservation, as ma va1 plus mb vb1 is equal to the combined mass of, say, the meatball plus the plate of spaghetti, or whatever two bodies, times v2, the combined mass's final velocity. For completely inelastic collisions, I like to picture vehicles that collided and got smushed together, sliding off in some direction neither of them was traveling. So let's do some examples here, working with these concepts of inelastic and elastic collisions, knowing that for elastic collisions, momentum and kinetic energy is conserved. So here's our first example. It's not going to be a written prompt. It's just this picture. You might be able to imagine that this is a simplified drawing of some more complex written prompt that we usually get. But it gives you everything that we need, and we're skipping maybe some of the interpretation, but we're going right to the scenario here. So we have initial velocities of each mass, and we have the masses of each mass. So there are springs on the blocks, and the surface is frictionless, so that this is a completely elastic collision, and momentum and kinetic energy then are both conserved. This is also a linear collision, so we only need to worry about momentum and motion also in the x direction. So where we would start is by writing our conservation of energy equations and momentum equation. So I'll start with momentum, and I'll say P here. So P, do that. The ma VA1 plus MB VB1 is equal to MA VA2 plus MB VB2. So that's from conservation of momentum. And then kinetic energy, I'll do this, KE. We have 1/2 MA VA1 squared plus 1/2 MB VB1 squared is equal to kinetic energy of both combined after MA VA2 squared plus 1/2 MB VB2 squared. So those are our two equations that we have that we know are true for this scenario. And what we're trying to solve for is the final velocities. So VB2, VA2, and we have each of them in both equations. So theoretically, here we have two equations to solve for our two variables, VA2 and VB2. So you can cross out all the 1/2s in the conservation of kinetic energy equation, because there's 1/2 in every term. You can solve for one of the variables, your choice, plug it into the other expression, then use that result to find the second variable. For those of you that want a challenge, you can go ahead and pause the video and spend 2 to 3 minutes, but no more than that, just proceeding with this. Go ahead and try to solve it. It's solvable. But it turns out that the algebra gets pretty nasty, pretty complicated pretty fast. And it makes for quite a nasty quadratic equation to plug in for and solve. And so what we're going to do is we're going to pause this example, and we're going to do some of the hard algebra work here in this video, and then leave you with some useful equations to use in the end. And then we'll come back and we'll solve this example. So we're halting work on this example, and we'll come back to it after we've worked with these equations just a little bit, yeah? So I'll switch to a new color for good measure. All right, so let's say, this is not the example that we had said, but just to start simpler, let's say object B is at rest when it gets hit by object A. If that's the case, then the kinetic energy equation becomes, so if B is at rest, then there's only kinetic energy in A to start. But there's kinetic energy, presumably in both, after. B VB2 squared. So that's our kinetic energy equation if B starts at rest. And our momentum, right, this is from conservation of momentum, not anything to do with potential energy. So momentum would be only A has momentum, so VA1, and that's equal to MA VA2 plus MB VB2. So these are our two equations if we have that scenario where A is colliding into B where B was at rest. So in this case, we can in fact solve pretty reasonably for the final velocities of both the objects in terms of the masses and the initial velocity of A. That's what we want, right? Because we're usually given initial velocities and the masses, and then some collision happens, and we want to see what happened. What are the final velocities of the colliding objects? So we can do that in this scenario pretty reasonably. So let's rearrange the kinetic energy equation. Kinetic energy rearranged. So we're going to kind of work our way towards solving for the final velocities, and we're going to choose VB2 to kind of get on the left side and everything else on the right. So we have 1/2 B VB2 squared equals everything else. So we have 1/2 MA VA2 squared minus 1/2 MA VA1 squared. That's fair, right? And then we can go one step further with that. So that, we can pull out the MA, right? So MA, oops. VA1 squared minus VA2 squared yeah, VA1 minus VA2. Yes, okay. And then we can go even further than that and say MA, multiply that out here, I'll do it up here. So final rearranged form is going to be this equal to MA VA1 minus VA2 VA1 plus VA2. Correct? And then momentum, we can rearrange momentum just the same. So rearranged momentum, we're going to solve for that VB2 term again. So we're going to get that term over on the left. So MB VB2 and set everything else on the right side. So we have MA VA1 minus VA2. Alright. So now we're going to divide the momentum equation, this guy, into the kinetic energy equation, into this guy. Right? We can divide one equation into the other. And what you get is this. VB2 is equal to VA1 plus VA2. So I want you to jot that one down with a little box around it so that you know where it is, so that when we come back to it and refer to it, I'll refer to this one as our little equation here a couple times. Because it's nice and simple, 3 simple little terms. So we're going to come back for that one later. But in the meantime, we proceed. So we're going to take that equation and we're going to plug it right back into this guy here. A rearranged momentum equation. Alright. So, if you do that, then you get MB. Here, I'm doing new color just for interest's sake. Huh? MB, and then the rest of this, right? VA1 plus VA2 is equal to MA VA1 minus VA2. Alright, now what we want to do is we're going to solve for this VA2 term for both of them. Right? So we're just going to do some rearranging. So we're going to multiply this out. MB VA1 plus MB VA2 equals MA VA1 minus MA VA2. And we're going to get both the VA2 terms on the left side. So we have MB VA2 plus MA VA2 is equal to MA VA1 minus MB VA1. Then we're going to pull out the VA2 here, so we have MB plus MA times VA2 is is equal to ma minus mb va1. And then we'll just divide this over. So you're left with va2 is equal to ma minus mb over ma plus mb times va1. Okay, so this equation is a useful result that you can use if B starts at rest, right? We've solved for the final velocity of A. If A collides into a B, which is at rest, and we solve for it in terms of just the masses and the initial velocity of A. So that's useful. But you have to know that it's only applying when B starts at rest. So then we can use this to plug back in and solve for the final velocity of B. So if you do that, so we have VB going back to our little equation here, this one. We're going to take this, we're going to plug it in right there. Yeah? So VB2 is equal to VA1 plus this whole thing, MA minus MB over MB plus MA. Just switched them. VA1 for no reason. Then we're going to pull these out. So that's going to be equal to 1 plus MA minus MB over MB plus MA, all that times VA1. Then we're going to get a common denominator here, right? So equals MB plus MA over MB plus MA, just to be explicit, plus MA minus MB over MB plus MA. And that's all, again, times VA1. So now we can combine these things, and we have the MBs canceling out here. So we have VB2 is equal to 2MA over MB plus MA times VA1. All right, so there we go. Now we solved for VB2, the final velocity of B, the object that started at rest in this case, in terms of the masses and the initial velocity of A. So there we go. So there's our two equations that are useful for when body B starts at rest. All right, and then one further. How about if A and B have equal mass and B started at rest, just the same as we just looked at, but the masses are equal? Well, if the mass of A is equal to the mass of B, then our first equation here makes VA2 0. And the second means that this is the same thing. So it would be MA plus MA, and then that's 2MA over 2MA, so that's 1. And so then VB2 is equal to VA1. What does that mean? That means that A came to a complete stop at impact, and B now has the same velocity that A had. So in other words, B received all of the kinetic energy and left A with none. That's if their masses are equal. This happens a lot in the game of pool, because the balls all have equal mass. And it also explains the Newton's cradle demonstration that you may have seen. So that would be this guy here. It's not animated, but you'll probably have seen this before. And if you haven't, Google Newton's cradle, and you can see some cool demonstrations. And it has everything to do with equal masses conservation of momentum, and elastic collisions. So that's what we're dealing with. So Newton's cradle should be able to be understood by the end of this, by the end of studying this lecture. Okay, so neat, you say, but we didn't derive anything useful for the problem that we halted work on, right? Because B did not start at rest for our example. So touche. So let's go back to this equation, the little equation that I said to box in. I'll write it again here. Pick a new color. So that was VB2 is equal to VA1 plus VA2, right? So I'm going to rearrange it. So we have VA1 over here and everything else on the left. So that would be VB2 minus VA2. So VB2 minus VA2, this part right here is relative velocity. That's the velocity of B relative to A. So whatever these two velocities are, if you take the difference of them, you're just getting the difference of the velocities, the relative to velocity, what the velocities are relative to each other, right? So it's the velocity of B relative to A after the collision, which this equation says is equal to VA1, the negative of the velocity of B relative to A before the collision. So in lecture 3, I told you it would be worth your while to read the section on relative velocity. For those of you who did, you might get more out of this than those who didn't, but follow along anyway, and I think it'll make sense. So the relative velocity has the same magnitude, but opposite sign, before and after the collision. The sign changes because A and B are approaching each other before the collision, but moving apart after the collision. If we view the collision from the perspective of B, you hop in and you are now block B, the one that started at rest, then the velocities are different, but the relative velocities are the same, if you can picture that. So thus, our statement holds for any straight line collision, even those where one body starts at rest. So relative velocity. So the takeaway for this is a nice result that will help us dramatically with these types of problems. In a straight line elastic collision of two bodies, the relative velocities before and after the collision have the same magnitude but opposite sign. So if B is moving before the collision, the expression just becomes VB1 2 minus VA2 is equal to the inverse of VB1 minus VA1. So these are relative velocity quantities, right? This is the relative velocity after and the relative velocity before. And so what we came to was that the relative velocity after is just the inverse, but equal in magnitude, to the relative velocity before. This is for elastic collisions. And it turns out that a similar vector relationship also exists for elastic collisions in general. So that's even when both bodies have initial velocities like we're talking about, and the collision is not restricted to one dimension. So this is an in general conclusion. So this means that we have an alternative equivalent definition of elastic collisions. In an elastic collision, the relative velocity of the two bodies has the same magnitude before and after the collision. So if this condition is satisfied, the total kinetic energy is also conserved because it's an elastic collision. So it's an alternative equivalent definition of elastic collisions. And we have this equation, which is very, very, very helpful in solving problems like the one that we halted on. So now we have the equation that will help us to solve the examples we began earlier, or the example. we have two equations that allow for much simpler solving. Our relative velocity equation, this guy, and our conservation of momentum equation from before. So let's go with these two equations instead of the kinetic energy equation, which had squared terms, which made it a little more difficult. So our relative velocity equation, right here, so VB2 minus VA2 is equal to negative VB1 minus VA1. And then our momentum, so I'll say relative velocity equation, and that's for elastic collisions. And then our momentum equation. So MA VA1 is equal to MA VA2 plus MB VB2. And in our case, VB1 was 0, right? So now you have a system of equations that is much more moderate to solve. There's no squared terms and odd things going on. And so if you solve that, which I advise you should just to ensure that you can do it, and to feel that power of solving a math problem, right? So VA2, you should get, is equal to negative 1 meters per second. And VB2 is equal to 3 meters per second. And just as our relative velocity equation has asserted, it turns out to be true. So basically, the relative velocity after is 4 meters per second. And the relative velocity before, if you remember the scenario here, put this back up. This was the relative velocity before, was 4 meters per second, right? But it was a negative 4 meters per second because you take VB1 minus VA1. That's relative velocity. B minus A, right? That's what we were doing. You just have to be consistent. And so it's the inverse and equal in magnitude. So they both bounce back and move away from each other, but block B is moving at 3 times the speed. That's what ends up happening physically. The relative velocity, VB2 minus VA2, is 4 meters per second, equal and opposite to their relative velocity before the collision. All right, so let's do one more example here before we call it quits. This is going to be an inelastic collision example. So here's our question prompt here. Straighten it out just a little bit maybe. Okay, there's our prompt. So a 1,000 kilogram car traveling north. So we have a direction, but it's in terms of north. So we just have to assign some coordinate system, right, according to north, south, east, west. At 15 meters per second, collides with a 2,000 kilogram truck traveling east at 10 meters per second. The occupants wearing seatbelts are uninjured. It's cute that it tells you that. But the two vehicles move away from the impact point as one. The insurance adjuster asks you to find the velocity of the wreckage just after impact. What is your answer? So again, we're searching for final velocities. But this time, it says that they move away from the impact point as one. So that means that we have a completely inelastic collision. Right? It's not just inelastic, it's completely inelastic. And that means that the two cars are sticking together and they're moving off in some new direction. So we know this is a completely inelastic collision. And so we know we're going to use this equation here. New color, new problem. So MA VA1 plus MB VB1 is equal to their combined mass MA plus MB V2. what we're trying to solve for is this here, this V2. Right? You can stick with A and B. You can say C and T for car and truck. Whatever you do, be consistent and make sure that you know what each subscript means, because this is easily confused when you get all these subscripts going on. Okay, so let's draw a picture, a before and after picture, to see what's going on here. Huh? So if we do it in little axes here, this is going to be before, all right, before, and we're going to say this is Y, or north, and this is going to be X, or east. And our, here, bring it right back into view here. Our car is traveling north, and the truck is traveling east. So if this is the before, car is traveling north, so the car I'm going to put here, and I'll do it in color. Do pink car, and it's traveling north at 10 meters per second, and it has a mass, so MC, I'll go with C and T for car and truck, and so therefore we'll do VC1, so the initial velocity of the car is equal to 10 meters per second, this direction, and MC is 1,000 kilograms. All right, and then we have a truck. So let's do greenish for a truck, and it's going east. So we're going to start it over here. It's a little bigger than the car. And so VT1 is the truck's velocity is, oh whoops, I wrote the wrong velocity. So the truck's velocity is 10 meters per second, and the car's velocity is 15 meters per second. So the car is going faster. All right, and then the mass MT is equal to 3,000 kilograms, right? Yes, 2,000 kilograms. 2,000 kilograms. Okay, and it's traveling this way. So that's our before. That's everything that we need for before. And so they each have individual momenta, and they each lie right along the axis, right? So the total momentum of the system, if we treat each of these as existing within a total system, in the y component of the total momentum of the system is entirely the cars, and the x component of the total momentum of the system is entirely the trucks. So that makes it a little bit easier when we get to figuring this out. So now let's do our same coordinate system and figure it out for after. So we have y, or north, just the same. And we have x, or east, over here. All right, I'm going to scoot all this over. So now what we have is the two cars have collided. So we have the car here, and I'm going to do this. That's the car. And then we have the truck that's collided with the car. Like this. And the masses have now combined into one total mass, and they have some singular momentum of this total mass. And if the car was heading north and the truck was heading east, when they hit, their momentum, they're certainly not going to go this way, right? And odds are they're not going to go that way either, right? Or that way. They're going to go somewhere. They're going to go somewhere in this quadrant here. So the momentum is going to be this way. And there's some total momentum vector there. And all that we want is to find that vector, because within that vector is the combined mass, right? So I'll just do mass times V2, right? And this is what we want. So if we can find this final momentum vector, then we can find the magnitude of V2 and the direction of V2. So there's going to be some angle here that we can define this momentum vector in terms of east, or x, and all we're looking for is the final momentum vector. And so it has x component and y component, right? Just like we worked with many times before. So this is px, and this is py, right? So that's our situation. That's our situation. So just like we learned, here I'll kind of put both of these on the screen. Just like we learned with projectiles and the motion in x and y for projectiles, the motion in the x direction is completely independent of motion in the y direction. This means that the momentum in the x direction before the collision is the same as the momentum in the x direction after the collision. And same for y as well. The momentum in the y direction before the collision is the same as the momentum for the y in the after. This is harking back to the concept when we were thinking of firing a bow and arrow or a bullet directly horizontal and dropping a bullet right next to it and seeing which one hit the ground first. They both hit at the same time because motion in the x is completely independent of motion in the y. So this carries over just for momentum just the same, because momentum is just mass times velocity. So it's a similar thing. So let's find the before momentum in the x and the y, and then that will tell us the components of the momentum in the x and the y for after, right? And then we can get the final momentum, complete final momentum vector at whatever angle that it's at. They made it a little bit easy on us because the truck is the only thing with momentum in the x, and the car is the only thing with momentum in the y. So momentum in the x from before, which is equivalent to the x component of the total momentum after, is equal to m, the mass of the truck, vt1, and the momentum in the y before, which is equivalent to the component of the total momentum in the y direction after, is equal to the mass of the car, mc, vc1. So now we have our two component vectors, and we could just solve for the magnitude, or find the magnitude, like we would with any component vectors, right? We take the square root of the sum of the squares. So px squared plus py squared, which is equal to the square root of mt vt1 squared plus mc vc1 squared. All right. So what that gets us is the final momentum, right? And that's equal to the combined mass, right, times v2. And what we really wanted to solve for was v2, not the final momentum. So what we're going to do is we're going to divide this final mass over And so then we'll end up with V2 is equal to this expression up here, Vt, Vt1 squared, plus MC, Vc1 squared. That's all under this radical, divided by the total mass, which I've been using as capital M, but what it really is mt plus mc. It's the combined mass of the truck and the car. And if you compute that out, plug all those values into your calculator, you should get that the magnitude of the final velocity of the combined mass truck, car, system object is 8.3 meters per second. 8.3. We're not completely done yet because we have to find the direction. So the angle that we defined theta in terms of the eastward direction, our x direction here. So now we have to find theta. But we have each of the components. So we're going to find theta using the tangent operation, just like you would with any components of a vector, right? So theta, I'll do white since the angle was written in white. Theta is equal to the inverse tangent of py over px, which is equal to the inverse tangent, to write it all out, of, where's py? Py is mc vc1 over px, mt vt1. So if you work that out, plug that in, make sure you're in degrees, not radians, then you get 37 degrees, which means that the direction that the wreckage goes after collision of this truck and the car is 30 degrees north of the eastward direction. So 37 degrees, we weren't too far off. So it might actually be something like this, that direction. And that's probably to do with the truck having more mass. All right, that is it for this video.